Good afternoon. So today we will continue with histogram. During last class, we end here. If we have more samples, what change? Okay. If we keep our beings, basically the number of beings, what is the range of each beings? We keep that the similar. We more or less we get a very similar shape. Okay, but if we have a much more sample, one thing we can do obviously is to make our each being to be more granularity. So basically, before each being, let's say, cover a range 10, you can separate that, split that into several. So one obvious outcome you will get a much detailed histogram. Okay. So as I already give you the answer, what we try to approximate here is a Gaussian distribution. So it's some kind of like a bear shape curve. So this is our underlying distribution. Of course, this underlying distribution is hidden from us. We have no way to know. We can only estimate from observations. Yeah. So the more data, the better way you measure your observation, probably the better estimation you can approaching your true distribution. So that's a goal here. Okay. So if we have more data, as you can see, remember our hidden oracle here is a bear shape. As you can see, if we're adding more data, we are approaching that bear curve. Okay. So I think we have talked about this part. So now we need to make a decision now is to how to choose those parameters. There are several parameters here, right? If we counting for example, the number of beings you want to choose, right? And also even the number of samples you like to collect, they are all type of parameters. So basically, the number of beings, the size of beings, or even the number of samples, we can all consider them as parameters. You need to make a decision right before. So usually, the number of beings and the size of beings, they are kind of related, right? After you make your data collection, you will roughly know what will be the range of your values. So if you decide, say, hey, I want to pick a specific value for the being y, so the number of beings more or less will be decided. If we are assuming a homogeneous being, so each being will take a very similar range. All right. So of course, the beings do not need to be homogeneous, but in this class, we will more or less focus on each being have a very similar or have the same range. Okay. So there's in fact, in literature, there's many ways to decide to choose the N and W based on samples. There's many ways. Each of the scheme here has a motivation or has some reason at the back. For example, you can take a square root. You say, okay, if I know the M here is the number of samples. Okay, if I know there's so many number of samples, the number of being I going to decide will be square root. Then I take a ceiling of that. And there's another formula is try to say, okay, how about I take a log 2 of your number of samples and then plus 1. Each of them, of course, they arrive at this particular form with a reason. So, but what is the optimal choice? Okay. Of course, in terms to define the optimal, we need to say what it optimal for, right? In terms of it's a visually appealing or in terms of what. So in this class, we will try to talk more about in terms of mathematical optimality. Okay, so before that, I think that we have already talked about the bin-wise intuition to say why the bin-wise matters to us. Okay, as I try to say, okay, if you have a large bin size, okay, and you may have a very coarse description about your data. If you, here we assume we have fixed number of samples. If you make your bin size very big, you may have a very rough estimation. Because remember, for example, if we are measuring a bear curve here, if you have a too huge bin size, you will have a very rough estimation. So it's not super close or approaching your true underlying distribution. But if you make a super small bin size, you can see here, first of all, probably a lot of bins will end up with 0. And also it's kind of noisy, spiky. And if you're thinking you are approaching a bear curve, again, there's a lot of error. So there have to be something in between, something to be, we call, let's say, beta or optimal. Okay. So how do we choose a bin size in general? So this is what I try to say in how to define optimality. Yeah, how do you think? I give you one histogram, I give you another. Which one is better? Yeah. So as I mentioned, maybe you can say, hey, this one looks visually appealing, or this is less appealing. That is fine. And also, of course, you want to use usefulness, right? You want to say the good histogram need to be more useful. But again, how to quantify? Because we are doing data science. We want something to be has a particular measure, you best with certain numbers. So which make us to arrive at the mathematical matrix. How do you derive a mathematical matrix to define this histogram is better than the other? When I say this histogram in terms of different parameters, okay. So I choose 5 bins for this histogram, I choose 10 bins for this histogram, given the same set of samples. Okay, so I need a way to say, hey, this 5 bins is better than this 10 bins. Okay, that is what we try to do next. Are we clear with the motivation here? Okay. So for example, this is a given. We have 25 bins, we have 5 bins, we have 200 bins. As you can see here, which one looks prettier? Obviously, like a 25 bins looks a better choice in this situation, right? But a lot of time this is of course visually we can using a visually checking. This is obvious, but 24 bins or 25 bins or 26 bins probably there it's hard to clearly see the difference. So we need a measure to tell you, okay, 25 is optimal. All right. So that is what we're going to do next. So here, there's two concepts. I think that we already see this. Is one is your estimated model, one is your true model. The true model is like a last class. I think I use the example of Indiana people's height. Right. The true model is you need to really try to measure each individual. but that is impossible or it's too costly. We won't do that. So there's no way to know the true distribution. We can only try to approximate that. We try to do a very educated guess to that. So what to do is we try to take samples, right? I take this class, I measure each of you in the class. I say, hey, this is a, maybe at least is an educated guess to the true model. So that is a estimated. We try to do here. We try to estimate or get a histogram from a small sample, try to approaching the true underlying distribution. So we have a true underlying model, which unfortunately is unknown or hidden, because unless you measure every single people in Indiana, you have no way to know what that true model is. So it's always hidden or unknown. But after we collecting data, like I measure each of you in the class, we are able to, or we are only able to estimate the distribution. We have something, we have a histogram. So we say, hey, this is a very, maybe a reasonable approximation, but how good is that? It really depends on how many beans you choose, right? How many samples you collect, those things here. So histogram are an estimate or approximation of the true distribution. So usually you can see here, we're using the hat here. Using, if you can see, we're usually using a hat to denote approximation or estimation. This is many people like to do that. Yeah. So if you see a function f, which you usually say, hey, this is a true underlying function, then you have a function f hat. That is probably indicates a approximation to the true function. Okay. So we have two things here. We have f. This is the true underlying distribution, and then f hat is our estimation. So basically, this will be our f here, right? It's a beautiful, perfect curve. This is a Gaussian. Actually, this is a Gaussian distribution, but there's questions. Yes. Sorry. Both. You mean this guy? Yeah. So in order to get this, if we want to visualize something like this, you need to have a huge amount of samples. Yeah. When we generate this, probably we generate a lot of samples to plot this histogram. So this is almost approaching the true distribution. Yeah. And this is a more the f hat we are talking about. Right. So when I plot this beautiful curve like this, usually I will think this as a true distribution, but of course this is a computer. So actually we generate this figure from a lot of numbers. Because this is almost perfect. This is a perfect curve already. So basically, in conclusion, both of them are generated from samples, but you can think the first curve something approaching the true distribution, which is usually we don't have. Yeah. So the second one is more or less what you usually will see. Yeah. With a limited number of samples, you will get something like this, a little bit sparky. All right. So how to quantify or how to mathematically measure how good is your histogram? Right. So again, I just try to refresh your memory. So now the histogram we will understand as an estimation of your true underlying distribution. Okay. Are we fine with that? So this histogram is just what you have in reality. And what we really want to model, what we are interested is this orange curve, this perfect bear shape. Okay. The reason why, again, for people who missed from the last class, the reason why this is a Bayer curve. Is just because in this particular example, we using the Gaussian distribution as an underlying distribution. Yeah. So of course we can replace this distribution assumption with another distribution. So you will not get a the Bayer curve. You will get some other shape. Yeah. So the reason you see a beautiful Bayer shape is just because our assumption. All right. So we know the unknown. So this is something which actually we don't suppose to know. This orange curve is something usually is hidden there. We don't know. We have no idea. But here, because we want to teach you about this, we try to disclose. Okay, this is the underlying distribution. Okay. So by pretend we know this orange curve, and what in reality what we really have is those those blue histogram. So now we want to say, if you already know this, pretend to know this orange curve, how to measure, how good is this histogram? This will become very easy, right? So you just basically try to measure how far away your histogram deviate from your orange curve, right? So this can be easily measured using something we call integrate square error. This looks like scary, but if you really take a close look, it's very simple. So this F, this is a orange curve here, is the true underlying distribution, is something we usually don't know. Okay, but we put here, which I pretend we know. Okay, and this is a histogram. This is F hat, is an estimation. It's like I measure everybody's height. We try to say, hey, this is a histogram we can get. Then this is probably the distribution of all Indiana people's height. Okay, so this is what we get from your limited observation. Then the X here will be your X axis, right? For each value, let's say you look at the this guy, look at this value, and say, okay, for the blue, so let's look at this value. Okay, so if I take this, let X to be here, so your blue bar is here, your orange bar is here, then I will take the difference between these two values. So this will be my difference. And because I do not care you are larger or smaller than the true distribution, I only care about how far you are away, you are deviate from the true model. So which reason I raise to power square, I remove the sign. Does that make sense? Okay, so you have a value here, you have a value here. I only care about difference. So I take the difference, then I raise to power 2. So I only care about the magnitude. So, and this is the difference only happens at a particular point at this location, right? But what I care is the total is a whole area. So I care about all the difference across the whole axis. So what I do is I integrate over X. So the final result will be a total difference, or we call the integrated square error. Any question about this integrate square error? Are we fine with this concept? Please just feel free to ask. We're fine, right? Also, the reason there's another reason why we take a square 2 here. I think that in machine learning we like quadratic form. Why? Because later you will see, I think that you will see many examples in this class. The reason is that when you take a derivative of a quadratic, you get a 2 multiply a linear form, right? So that will simplify a lot of stuff. Yeah. Sometimes we are more interested in some even 2/2 of a certain square. Yeah, this why? Because you're able to cancel out the 2. Yeah. So this is a very favorable This is integrated, but a lot of time we usually, if we are interested in discretized version, we will do you will replace the integration with a summation. You are sum over a sequence of discrete numbers. So you will see more examples later in this class. At first, I mean, I hope everybody feel comfortable with this integrated square arrow. This essentially try to measure what you have observed. The model from what you have observed, how different it is from the true underlying model. And the true underlying model, unfortunately, is unknown. Okay. So how can we compute this arrow? Because fx is unknown. It's not easy. Yeah, it's not easy. And next, we will present you some method. Is a little bit. Yeah, there's a lot of detail is skipped here. But I will try to present what you need to know on these slides. Then I will give you a little bit explanation, which you do not need to know, but I just hope to remove some of your confusions or remove some of the myths here. Okay. So what you need to know, yeah, I guess maybe some of the homework but anyway, you need to know is probably the following. Since we are interested in to measure this error, all right, and then pretend you trust me, and without understanding the step, this arrow can be written as another criteria, JW. So the W, what is W here? The W is the width of your beam. Right. Remember, we have a few parameters here. The width of your beam, okay, the number of your beam, the number of your sample, right? So here, let's pretend we already fixed the number of our samples. So you already finished the data collection. I already measure every of you's the height. Assume I already did that. Okay. So then now what I have is I know what is the minimum of your height, what is the maximum of your height. So I know the range of your height. So maybe the shortest among you probably 1.5 meter. Then the highest among you maybe 1.9 meter within your range. So I can take that range, then divide by something. Divide by what? Divide by my W, right? So as long as I know what is the width of your beam, if I take that range, divide by this, I will get the number of my beam, right? Is that clear? So essentially now everything will end up with deciding what is the optimal size you are choosing for each beam. Are we okay with this? Okay, so great. So this is a reason why we want to write our objective function as a LW, as a function of W. The W is the undecided, is the what is the width you want to pick for each beam. So if I change my W, for each different W, I will have a slight different arrow, right? So this is a background. So what we try to, or what you need to know is, first of all, this can be written as another function plus a constant. So this actually can be very easily see. I will show you some additional notes next. Yeah, but remember, we are writing the LW as a JW with another constant. And then the JW can be write as a forward. Yeah. So let's for now, let's do not try to understand, just try to see what is here. So the W here is the width of your beam, okay? And the M is the number of samples, which is the M is your number of samples. And then the other P hat is the beam probability. So actually this equation is very simple, right? Although looks like the other step to arrive this is very mysterious. But actually the equation itself is very simple, right? You know what is a M, the number of samples, you know what is a W, the bin wise, and all this P hat is your histogram probability. This is very easy. You plug in, you will get your JW. Right, is that clear? So for now, please do not try to understand this. Just try to see, are you comfortable with this JW, how to compute the JW? I believe you are comfortable, right? You are plugging a few things, okay. So if I change the W, I say I start W equal to, let's say 2, then I change my W to 3, change W to 4, for each of them, because M, we fixed for now. And for each of them, we are able to recount the number of counts, right? After you change, you can recompute all your P, right? What is a P? What is a PK? The PK is just the count within a particular bin divided by the total count, right? This is your probability. We have seen this last class. Remember, the fraction of the samples you fall into that bin. So basically, we change the W, you will have a completely different JW. The JW is a value. You will have a different value. So you have a measure to say how good is your W. I hope everybody feel comfortable about that part. Okay. So allow me finish a few slides, then I will come back to re-explain why we have this. So now we can choose the optimal bin by minimize JW, because the JW is the difference between your histogram and your true distribution. So we want to find a W that minimize your JW. All right. Any questions? Any question about these slides? Why we do calculation in this way? And what is W, what is M? Yes, questions. What concept are we? Oh, yeah. Actually, I was showing you, but if you're curious and you can try to expand this quadratic, right? This will expand this quadratic, you will get this and 2fm, sorry, 2fmf, then plus f square. And you can see this guy does not depend on W at all, right? So this will be that constant. Because this guy depends on W, this guy depends on W. So you are writing this integrated square arrow in terms of something depend on W, something complete independent of W. That will be your constant. Yes, questions? No, this distribution does not depend on normal distribution. Yeah, this is a general measure. You mean this guy, right? This actually, I will show you. The reason you get this is through something we call cross validation. We do not assume the underlying distribution. So, but for now, I think that your responsibility is just to make sure you are able to compute. How do you compute the JW? That is your responsibility. All right, great. So now at least we know if we change the W, you will get a different J value, right? So one of the easy way to find the optimal W is using brute force. Basically, you are iterate over all possible W. For example, you start your W. Of course, here in this particular example, we are trying to using the number of the bins. But as I mentioned, if you know the range of your values, know the number of bins or know the W, which is essentially the same thing. All right. So here we try to say, hey, let me try to start with 0 bins and then 1 bins, 2 bins. whenever you pick a value for n, you're using a range divided by n, you will get your W, right? So you are able to plot a shape here. Looks like you are decreasing, then increasing. Looks like this point will be your optimal value. Looks like that happens when n equal to probably 1 or 2 in this case. All right. So basically you are searching through all possible n's and then pick what is the minimal j. So this is the brute force case here. So again, you pick different n. For each n, you compute your W, plug in into this formula, right? Because for each, once you decide your n, and you are able to calculate the histogram, right? So you are able to plug M and plug W with your computed histogram, you are able to get a J. Then you will plot that J. You plot a sample of N versus J. Try to find where to plot. Maybe it will be here, or be here. Then you iterate over all N, you will say, hey, at which time the J is the smallest? Then that is probably your optimal choice. Are we fine with this concept? Any questions? Okay. So of course, this brute force looks like a little bit less efficient. So usually in this situation, or in general, if you have no better way, you have to do a brute force search. This, of course, is not a very pleasant choice, but one method can help you a little bit is to do grid search. Is to do not like iterate over each single one, but try to make your incremental step to greater than 1. So let's say I want to choose every 2. So basically I start to say n equal to 0, then n equal to 3, n equal to, yeah. So basically you do a grid search. That will be a little bit better. Yeah. But if you have a lot of more parameters, grid search will be a very, very good choice. If you, let's say you want to search over 3 parameters, right? If you iterate over every single value, basically you have a 3 loop, right? Then you will reduce your search space by cube. That will be a very fancy. Yeah. If you have more parameters, then that even better. But of course, for this single case, looks grid search will help you a little bit. Yeah. All right. So I want to show you this. For this part, you do not need to know anything at all. I just write a very small notes, try to help you understand a little bit what's amiss here. So first of all, this is actually address the gentleman's question to say what is the constant. So we have a quadratic form here. We have a quadratic form here, so we can expand it. So as you can see, this will become your constant. The last term will be the constant value. So what you need to care is only the first 2 guys. So basically your JW will be in this form. So the first one is easy, right? The first one is your histogram, right? Is your histogram. As I mentioned, the F hat is your actual histogram. Once you decide a W, you are able to compute all the F hat. Is because this is like the fraction of observations fall into a particular bin, right? And unfortunately, the second term is a histogram, but multiply with your 2 distribution value. This is something you don't know. The fx is something you don't know. Okay. So how to compute the second term? This is a more advanced step. And what we use something here is called a cross validation. So if you really look at this term, what is the best way to approximate this? This essentially try to say, I want to know, I want to multiply what you have in your histogram with the true likelihood associated with that particular point, right? So what we try to do here is a very cute strategy called cross validation. Is try to say, if I want to estimate what is the true probability for a particular point, I will take that point away and using everybody else try to compute the likelihood for that point. So I will use that as my measure here. All right. So basically, as I meant right here, so this guy is the histogram estimation obtained after remove the ice observation. So basically, you remove observation and using everybody else to compute this value. So basically, then after certain mathematical rearrangement, I will skip the detail. You don't need to know that. You will get the actual computation or actual formula we are showing in the slides. So I hope that at least bridge the gap a little bit. All right. So I think that we have time, so we will move to the next topic. Any questions about histogram? Otherwise, I will jump to the next exciting topic, probability. Yes, questions. Oh, yes. Oh, yes, yes. Actually, we include something slightly different, but more or less very similar. Yeah, because I plan to do that, but I see another instructor have already put a link to certain supplementary material. But you are not responsible at all to that node shift. That is just to help you to remove some of the mysterious. So the next topic is we will talk about the probability and the random variable. Okay. You will see after you see the concept of histogram is so natural to proceed to the probability concept. So what is probability? In general, we can think probability as a measure of likelihood that an event occurs. So a probability need to be a value between 0 and 1. So the high number, the more likely the event occurs. Okay. So a probability of 0 means an event never occurs. A probability of 1 means an event always occurs. Okay. So for example, what is a probability the event has when you flip a coin? Okay. So when you flip a coin, if this is considered a fair coin, you are expect to have the half time to have head, half time to have tails, right? So then the event of heads, the probability of that will usually assume to be 0.5. Right. If you're comfortable with this, you are more or less get the idea of this probability. So the probability is try to measure how likely a certain event occurs. Okay. When you roll a dice, let's say you have 6 faces, a particular number the probability of particular number or any of number associated will be like 1/6. Yeah, so something like that. So let's define experiment. So if you conduct an experiment, you will get outcomes, right? Just like you flip a coin, you will get a head or tail as your outcomes. Okay. So each outcome will have a probability between 0 and 1. And a set of all possible outcomes is your sample space. For example, when you flip coin, you will get head or tail. The head and tail will forming your sample space. All right. For example, in this figure, let's say if I are able to rotate my numbers, okay, and if let's say I keep my arrow fixed, so it's at the end after the rotation stops, this arrow will point to a number, right? So first, let's look at what will be your outcomes. All the possible outcomes will be numbers like 1, 2, 3, 4, 5 here, right? So what does that mean? That means your sample space in this case will be 1, 2, 3, 4, 5. That is your sample space. Because no matter how you rotate, you will end up to generate a particular number from my sample space. Okay. Then you take a second look at this rotation event. You will find different number or different ending number have slightly different likelihood. For example, the number 1 is probably, it will, because we have 8 portions here, right? We only have one of them as 1. So that means only 1/8 of the probability you will have the number 1. So basically the probability of 1 or the outcome 1 will be 1/8. Okay, let's say 3, number 3, you have what? You have 1, 2, 3. So basically you have 3 chances to have the needle to point you. So that means the probability of outcome 3 will be 3/8. All right, so are we comfortable with this concept? So then we define another concept called event. An event is a set of possible outcomes. For example, now I can define my event to be, let's say 1, 2, 3. So I want to say, what is your probability of an event, 1 or 2 or 3? Then that probability will be the sum of the probability of individual outcomes. So basically, the probability of an event of 1, 2, 3 will equal to probability of 1 plus probability 2 plus probability of 3. Yeah. So for example, here our sample space will be 1, 2, 3, 4, 5. All right. And then the probability of 3, as I mentioned, will be 3/8. And then the event 1, 3, 5 will be 5/8. Why? Because the probability of 1 will be 1/8. Probability of 3 will be 3/8. Probability 5 will be 1/8. So 1/8 plus 3/8 plus 1/8 equal to 5/8. So this is a sum of the probability of individual outcomes. Any questions about this? I mean, those are simple, but if you don't have those image in mind, you will soon lose track of things. Yeah. So those are very, very simple concepts, but make sure you know what exactly. If you before you have take some classes of probability, those are trivial, but if you never see those, yeah, this might seem a little bit dry to you. So are we fine with this? Okay. So this is a very good picture to visualize what we have taught. So we have experiment, we conduct experiment. and the experiment will give you outcomes. And so all the possible outcomes put together will forming your sample space. Sample space contains all the possible outcomes. When you flip a coin, you will get head and tail. When you roll a dice, you will get 1, 2, 3, 4, 5, 6. So those things will be your sample space. And then for each of the outcomes, you will have a probability. You associate with certain probability, right? And also you can try to group your possible outcomes to form an event. And then for those events, you will also be able to assign certain probabilities. All right. So this is those will be our target to study. Okay. Study the probability of events, probability of outcomes. Okay. So we have mentioned so far the probability will be, you can very loosely to understand as a measure of certain likelihood. Yeah. Okay, but what exactly or what is a more popular way or more rigorous way to think of a probability, but there's no common agreement. So at least there's a two popular category or two popular perspective to look at probability. The first we call a frequency. A frequency will try to think the probability as follows. You try to repeat the experiment over and over again, then the probability of an event will be the fraction of the time of a certain event happens during the experiment. So this is a more like what we see in our histogram case. You're just counting the number of people arrive, right? Then you try to put them into a bin and try to take the count, divide by total count. That looks like a fraction, how frequent a certain things happens, right? So this is called frequentist. So you repeat experiment and just see what is a fraction of the time certain things happen. Okay. And there's another perspective is called Bayesian. So in Bayesian, the probability is a reflection of your belief about the likelihood of something happens. So now the probability becomes a belief. For example, sometimes they both can explain things. When you flip a coin, why you say head, probability of head is 0.5. The frequencies will say, hey, you throw it millions of times, count the frequency, probably half of them, based on the half of the fraction of your time, you get head, right? But then if I'm Bayesian, I will say, hey, my belief is if you have a fair coins, half of the time you will get head. So this is the difference. And actually this do make a difference. In machine learning, this do make a difference. I think that I have 1 minute left. So I just want to give you a very quick, sometimes you end up with a slight difference. And especially when you derive machine learning models, you end up the difference will be some kind of a prior. The difference will be a prior. For example, I just give, this is a base rule. Yeah, this is a base rule. It's like let's think about let's think about a quick example. For example, let's say B will be say I see you have a running nose, and then the A will be your catching a cold. Say if I see your running nose, what's the probability of your catching a cold? So what does that mean? That means first you want to say, hey, if I catching a cold, what's the likelihood I will observe you to have running nose? All right. So this seems to already give you a good evidence to say how do I associate these two? But then there's another prior to say what is the likelihood or what is a belief or the catching a cold usually happens. So that is a prior. That is something which usually you will assume certain prior. Okay. So of course maybe this catching cold is not a good idea, but I hope give you a very rough idea. Yeah. So I see you next week.
Yeah.